So last time we wrote down the generic equations for an nth order polynomially interpolated element, and but it was just a single element, right? So now we want to see what we would do if we have a collection of elements or assemble them, right? So if we have a single element isolated out of a collection, meaning not one that's sort of got the boundary conditions associated. If we were to write a free body diagram of that thing, we would see that it has basically two n unknowns, right? So where n is the number of nodes, and so the unknowns would be the u's and the q's. So when we assemble a group of elements, we want to use the continuity in the u's and balance the q's to do it. So as an example, if we look at two elements, so the nodes are 1 and 2, and I'm going to have another element connected here. But what I'm going to do is I'm going to pull it apart, okay? I'm going to pull it apart so that I can write a free body diagram of each element individually, right? So this is also node 2, then you have node 3 here, okay? So each of these has some solution, U2, E1. So this is E1, E2, U1, E2, U2, E2. So those solutions are U1 over element 1, NJ, UJ, U2 over element 2, NJ, UJ. And then we have some Q1, E1, some Q2, E1, some Q1, E2, and some Q2, E2. All right. Well, so Q2, E1 plus Q1, E2 is going to equal 0, or rather, it's going to equal 0 if no external force is applied. Otherwise, it's going to equal QI if an external, I said force, but that sort of implies we're talking mechanics. Let's just say source to be more general. Could be a force or a flux. So it's going to equal QI if there's an external source of magnitude QI. Otherwise, it's going to be equal to 0. And there's going to be a continuity of displacement. So U2, E1 plus U1, E2 has to equal U2. So the displacement of node 2, I'm sorry, they have to be equal to 1. So each of these elements have some stiffness matrix, so we'll write it down just generically. So the stiffness matrix, if we assume that just a linear interpolation, it's going to have 4 components, where the superscripted 1 implies element 1. And element 2 will likewise have So when we assemble the global stiffness matrix, then we'll have so we have this term here where the two elements overlap. So, well, what?
It would be K superscript 2 subscript
1, 1. Sorry. 1, 1. So just so I don't have to rewrite it on the next page, we'll call this KG, K global. So we have K global, right, and it multiplies U1, U2, U3, the nodal displacements, or the nodal values we're solving for. And then on the right-hand side, we'd have F1, 1, F2, 1 plus F1, 2, F2, 2. So that would be, we're still working with our model equation, our generic model equation from last time. So we defined this F. These F is like the integral over the domain of some f of x in I dx, right? Plus our source terms. So if we look at an example, of a bar with an irregular cross-section, and of course in this case, if the cross-section is something that we can easily describe functionally, we should, right? I mean, the right way to do this is, in this case, as I have it drawn, it's sort of just a linear cross-section, linear with x. So we can write a function down, and we can do it that way. But let's just assume that, maybe there's some small irregular wiggles in there that we can't really not write a nice function down for, okay? So in that case, we might decide to, instead of modeling this as one element, where the cross-section is as a function of dependence on x, we might choose to split this thing up and just model it with multiple regular cross-sections. Right? And in this case, I didn't draw it very well, but in this case, let's assume that there are 3 elements of equal length. So 4 nodes. Each of the well, it's all made of the same material, so everything has Young's modulus E. Let's assume that all of the links are the same for each of the 3 elements. But they do have different cross-sections, so this would be A1, A2, A3, okay? So you should be able to see that this is sort of like the trapezoid rule in integration, that if we make these small enough, we'll approach the correct geometry. But I just chose to do it that way because we already know what the element stiffness matrix is for this geometry, right? So I don't have to rederive it. We can just write it down. So if we do that, right, of course, we have A1E over L minus A1E over L minus A1E over L. And then here we'd have A1 plus A2E over L minus A2E over L minus A2E over L. Here we'd have A2 plus A3E over L minus A3E over L minus A3E over L. Right, so this will be our global stiffness matrix, which multiplies U1, U2, U3, U4. And what's our right-hand side vector then? 0, 0, 0, P. And we can almost solve this. There's one last thing we have to do. If we want to solve this, apply the boundary condition, right? We have an essential boundary condition here. This is a fixed wall, so that displacement has to be 0. And we can do that by, the easiest way is to just put a 1 here and a 0 there. Then that first equation reads U1 equals 0. And so then we could solve this thing. So you might have a question